Note, this video is part of a larger series on speed solving the FTO. Click the playlist link in the description to see the rest of the videos. I'm super happy to have finally finished up something that I have been thinking about for a really long time, and that is an algorithmic approach to reaching the pair formation state in last three triples. What I have done is found the sequences of flips that you need to reach pair formation from any L3T state. And I'm calling this method OLP, or one-look pairing for short. The process of reaching the pair formation state is effectively the same as before when you were doing it intuitively, except now all of the sequences of flips have been optimized for ergonomics and for rotationless execution. This effectively means that if you use OLP in conjunction with the TCP algorithms, it allows you to solve the last three triples in only 2 looks. This is not something that I would have thought possible even recently ago, so it's pretty incredible. Let's jump into how it works. Every single L3T that you need to know for reaching pair formation can be distinguished by how many bottom triangles you have on your top face and how your corners are oriented. This actually gives a total of only 12 cases that you need to learn. Now for each of these cases, whether your triangles are in an even or odd permutation state also does matter, and as a result there are 2 solutions that you need to learn for each case. So as an example, here I have this case with one bottom triangle on top, these 2 corners are twisted, and my triangles are in an even permutation state, so I know that if I execute this solution, I reach pair formation without even having to think about it. Now on the other hand, if the triangles are in an odd permutation state like this, but I have exactly the same case, then this requires a different solution. But it's the same idea. Now I have come up with each of the solutions for reaching pair formation for these on my own, and I use 3 different flip algs in them. Of course there is the regular hedge and sledge that we already use, but there is also a third flip alg that I have included, and that is the inverse sledge or lefty sledge, and it looks like this. By adding in this third flipping alg into the solutions, it now allows them all to be solved rotationless, which is really nice. I have compiled all of the cases together into a single sheet and the solutions for them, and you can check this out through the link in the description of this video. For each I have provided a picture showing what the case actually looks like and how to distinguish it, the 2 solutions, one for each permutation type like I mentioned, and some additional comments. One other thing to note with these solutions is that, like before, 2 flip avoidance can still be used. When you get to your last flip in a solution, sometimes your bottom triangle may end up shooting into the slot that matches with it, which would be a 2 flip case. So if we were to do it normally, you can see that we get there. So I have marked the last flip of each solution with an asterisk. This indicates that you can swap between either doing a sledge or a hedge to avoid the 2 flip. So in this case, we want to do a hedge instead, and there we go, we avoid the 2 flip case. This is another reason that I chose the solutions that I did for each of these OLP cases. When you get to the last flip, you're automatically in a good orientation to either use sledge or hedge without having to rotate the whole puzzle and doing a flip from a different angle. Again, eliminating the rotations. Except at the very end when you have to form the pair formation, but unfortunately this is unavoidable. So once again, you want to always watch out for 2 flip and be sure you're avoiding it in solves. Now I will not be going through every single case in this video, but I will be showing a couple of example solves just so you can see how this works. Now I must give a few disclaimers before moving on. First of all, these sequences of solutions only solve up to the pair formation state. These are not one-look last 3 triple algorithms. And afterwards, you must use a TCP algorithm to then finish solving the puzzle. Secondly, and this is pretty important, don't learn all of these as algorithms. Think of this more like intuitive F2L for the 3x3 cube. You only really need to bother memorizing how each of the solutions start out, and from there it's fairly easy to kind of figure out intuitively how to finish them. So that's what I would go with. Lastly, as I mentioned previously, these sequences were found by myself, and as a result, these are only my recommendations. I encourage you to experiment yourself with each of the L3T cases to find your own solutions. You may find ones that are better suited for you. But with that out of the way, let's go ahead and take a look at some example walkthroughs. Alright, so let's say that we get to our last 3 triples and we get to this case right here. So as we can see, we have 2 bottom triangles on our top face, and we have these 2 corners here that are twisted. So if we look on the sheet, this is case 6A. Now here, because we do have a bottom triangle within our bottom two layers, it is important to note where it is. In my case, it's over here in the back. This is also an even permutation state on our triangles. And after some setups from the picture, you can see that this is actually where we do need to start holding the puzzle and how we need to orient our top layer. So now we execute the first solution, which in this case is going to be a sledge to start off, then a U prime like this, and then it would be a hedge. And we do need to check to see if we're going to get a two flip case. And in this case, we do not, because this is a yellow triangle and that's going to be going here. So we don't get two flips. So we can finish the solution with hedge, U, like it says. And here we are at pair formation. And now at full speed, that would look a bit like this. Once again, the advantage of using these solutions for pair formation is that they are optimal, rotationless, and ergonomic to execute. Now, from here, we could just finish with a TCP. So in this case, I have this one. So it looks like this. And we're done. All right, here's now that exact same sort of case, except this time we have an odd permutation on our triangles, in which case we need to execute the second solution in that sheet. And that looks like this. And we have pair formation. So from here, we just do the TCP, and we're done. All right, so now here's another L3T case. For this one, we can see we have one bottom triangle on top, and we have two twisted corners in the back here. So this is case 4C on the sheet. And looking at our bottom triangles, we can see we have an odd permutation state. So we're going to need to execute the second solution. So we can go ahead and start going into that like this. Now you'll notice here that when we get to this point, the sequence would normally say to do a sledge and then a U prime to finish. However, we can see that that's going to take this triangle over here and place it in this slot. And since these match, this is going to give us a two flip case. So for the last flip, since I marked it with an asterisk, we actually need to do a hedge instead to avoid the two flip. So we can do that. And then finish the solution like normal. And now, as you can see, we avoid the two flip case and we get a proper pair formation. So I hope this helps illustrate the process of using these sequences of flips to get to our pair formation and how to recognize them, avoid two flip cases and the like. So now I'd like to show an example where full TCP can really provide an advantage. So let's say we have this L3T case. As we can see, we have these two bottom triangles on top and these two corners are twisted. So this is case 6B from the sheet. And here, since our bottom triangles are in an even permutation state, we would need to execute the first solution to solve this if we're going for even TCP. But this solution takes two flips to get there, and if we were to execute it, it would look like this. And then we'd have to go into our even TCP alg after that. This means that if we know the odd TCP algs, it's going to be better to go for the shorter solution, which in this case is the odd permutation solution. So if we go ahead and do that, you can see that now we get an odd permutation pair formation. So to finish now, we need to use an odd TCP. But as you can see, this is a little bit better because we only needed one flip to get here and then one algorithm to finish. And there you go. So knowing full TCP, in other words, lets you choose the shortest of the two solutions for each case, which can really speed up solves. And learning OLP also means that you will know exactly which cases this is advantageous for. If the two solutions are basically equal in length, it's still usually better to go for the even pair formation, as those even TCP algs are just a little bit nicer. But when used to its full advantage, this technique can be really powerful. Alright, so now I'd like to give some tips for being able to look ahead into the last three triples case that you're going to end up with, so that you can reduce the pause before going into your OLP solution. So let's say that we've just matched up our last bottom triple here and we're ready to go ahead and insert it into the bottom layer. In this case, this is going to be this insertion right here. And then after that, we get left with our OLP. Now the important thing with recognizing all of these OLP cases is that you have to know where all of your bottom triangles are located. For example, if we look at this, we can see, well, there's one over here and one here. But is the third one in this spot or in this spot? And actually, as we can see, we know that it's going to be in this spot. But having to look and check for that takes some time. So if we go back a second, if we take a look at what happens in the middle of the insertion for this last bottom triple, after the second move, we bring over this triple that was in the back of the last three triples case. And we can see that this triangle right here is actually one of the triangles that is in that bottom slot. See that? So what we want to do is that as we go into our insertion for the last bottom triple, we want to look at this triangle right here as we do the sequence and see what kind of triangle it is. And in my case, this is a top color triangle because my top layer color is gray. So that means I know that when I finish the algorithm, that this triangle in the back right here is going to be a top color triangle. And you can see how this is useful, right? Knowing that and seeing these two bottom triangles here, that means that we know that we automatically have the last bottom triangle in this back right slot over here. Effectively, this is allowing us to look ahead into our OLP case, and this can make the solution go a little bit faster. So in this example here, I know that since this is the last bottom triangle, I have this pair and this pair. I just need to rotate to right here, do a hedge, and we're done. Now, if we have the other case for inserting the bottom triple, where the bottom sticker is on top this time, then of course we know the algorithm is like this to insert it. So this time in the middle of the sequence, we are bringing up this triple from the back right position. And if we look at this bottom triangle in the middle of the algorithm here, we can see that this is a bottom colored triangle, again, for my color scheme. So I know that when we finish, that this bottom triangle is over here. And seeing that I have these other two on top like this, then I automatically know where all my bottom triangles are. I automatically know which case I have, so I can just go ahead and go straight into my solution and finish just like that. So you can really see how powerful this can be, and it's a really simple trick. You just have to look at one particular triangle position in the middle of your bottom triple insert, and you automatically can tell where all your bottom triangles are for your last three triples case. And this can actually go even further than that. We can even recognize whether or not our permutation state for the bottom triangles will be even or odd. So again, let's say I'm inserting the last bottom triple, and I start this off, and I see, here's my bottom triangle, and it does not match with this edge sticker on this side. So I know that this triangle is not going to be in its correct slot. Now I finish the algorithm and look on top, and I see that I have this bottom triangle right here. And since this one is a top colored triangle, then I know my last bottom triangle is in this position. And if we know our color scheme well, we'd actually be able to tell immediately that this is an even permutation state. Since this bottom triangle over here didn't match from what we had before, then we know that our last bottom triangle over here also does not match. We can see that. So if we were to look around, you can verify, yes, this is an even permutation state. But we were able to do it from this angle without having to rotate the puzzle at all. Pretty clever. I can't really stress enough how important this look-ahead technique is for going into your last three triples. And now with OLP, it's even more powerful, so it's definitely something that you need to be implementing in your solves if you can. Alright, so now while this works pretty good, there are some particular cases where it's actually better to go for alternate solution types, and I'm going to go through some of these here to show you what you can do. For the first case on the sheet where you have no bottom triangles on top and all of your corners are oriented, there are other ways that we can solve this case that are a little bit nicer than just doing the hedge and then going into our algorithm. If you get a case like this, the first thing that you should do is orient your top layer correctly so that it matches like this, and then this allows you to recognize the actual case that you have a little bit easier. Now I'm going to go through each of the cases that you can get here. If you run into a situation like this, where all of your pairs match up, as you can see, then we can actually cancel into our 4 mover for the TCP and get a nice 7-move sequence for this case. If the 3 triples here need to cycle clockwise, like this, then we can rotate the puzzle to this angle, and then the algorithm for this is the following. And solves it. And for the case where they need to cycle counterclockwise, like this, then we can rotate to this angle here, and then the sequence for this is the following. Rotate to here. Just like that. Another case that you can get is where the corners do not match up with the bottom triangles like this, and you effectively have offset pairs. If the bottom triangles need to cycle clockwise, like this, then we can rotate to here, and effectively this algorithm now will cancel into the 8-move TCP. And it looks like this. Rotate to here, and then do the second half of the TCP. And solved. And for the one where they need to cycle counterclockwise, we rotate to here, and then do this algorithm. Rotate this way, and now finish with the TCP. And there it is. And here is the last one that you might see where your corners are solved on top, and effectively you just have 3 bottom triangles that need to cycle around. And again, this is an even permutation here. For this case, there's actually a really nice commutator that we can use. And so to execute this, we rotate to here. And if they need to go clockwise, then the algorithm is the following. There it is. And if they need to go counterclockwise, then we simply do the inverse of that, which looks like this. And there it is. Now those were all the even cases, but sometimes you'll get an odd permutation state on your bottom triangle. So effectively it kind of looks like just 2 have to swap, and then you may have your corners on top. In the case where your corners are not solved, then what you want to do is hold the puzzle so that the solved bottom triangle is on the left-hand side. And so we are going to be flipping the 2 unsolved triples, and this is really important. Now from here we want to effectively do the flip that is going to solve our corner permutation. So in the case where the corners need to cycle counterclockwise, that's going to be a hedge from this angle. On the other hand, if the corners need to cycle clockwise, then that is going to be a sledge from this angle. And what this guarantees is that we will avoid a 2-flip case, which is what we want. So now we have this odd permutation PF, where we have our corners permuted correctly. And so that means that this is the easy 9-move odd TCP algorithm, and we can just finish with that. Pretty cool. Now what about the case where your corners are solved on top? Well, you're guaranteed to just have 2 swapped bottom triangles, and there is a very simple commutator that we can also use for this case. We want to hold it either like this, with the 2 triangles kind of in our view like this, or we can hold it this way. It doesn't really matter. Effectively, our first move is going to be a F wide move like this, so it's kind of putting them in the back anyway. And this algorithm goes like this. And there it is, solved. So you can see for that very first case on the sheet that there are actually a lot of really nice algorithms that we can use instead to solve these cases, instead of going through the route of doing a flip and then trying to do a TCP. So these cases are actually pretty nice to run into. For both cases 2 and 3, you can often force a TCP skip on these, and I illustrate how to do that in a later video on the playlist, which is the CP skip video. So if you run into cases like this, then you definitely want to see if you can try and implement that. For case 3 in particular, there are some situations where there are only a few triangles that are left unsolved, and we can actually use a commutator to solve these really nicely. These ones aren't too hard to recognize. You'll have just 1 on top, and then you kind of have 2 in the bottom layer here that all kind of need to cycle around. For the first one where they have to cycle clockwise, we can hold the puzzle from this angle right here, and then do this algorithm. And that solves it. And for the case where they need to cycle the opposite direction counterclockwise, we can simply do the inverse. And here's actually another one you might run into where it's just 2 triangles this time that are swapped, everything else is solved. We set it up like this, putting this triangle in the back left and facing this other one. Holding the puzzle like this, we can then use this commutator. And it solves that one too. Cases 4A and 4B on the sheet are effectively 1-flip cases when you're going for an even permutation state. So for these, using full TCP will speed it up. Cases 6a and 6b are the same story, but I already showed an example of this earlier. Going for the solution for odd permutation states every time is going to be faster. Finally, case 8 on the sheet is one that can again be forced into a TCP skip every single time, and I do recommend that you do this. That's it for this video. Be sure to check out the others through the playlist link in the description.